Yeah, my name is Bob Bolton. I'm going to talk for Amy Breen about a project that we've been working on together, the integrated ecosystem model. This is quite a bit different talk than all the other talks I've been seeing this afternoon. But what I'd like to talk about is the ecosystem model, integrated ecosystem model broadly, and then a piece of the model that I've been working on, specifically the Thermokarst model. So what is the integrated ecosystem model? The IEM is meant to be a tool to help support decision makers in aid in understanding nature and rates of landscape change, illustrate how landscapes are expected to respond to climate-driven changes, and then the part that I'm working on, the Alaska Thermokarst model, is a part of this IEM project. The IEM takes into account changes in vegetation, changes in disturbance, either fire or thermokarst, hydrology, and changes in permafrost, which are driven by changes in the climate. So what are the components of the IEM? We've gone through 2 different phases. We're just finishing our phase 2. The initial IEM model is comprised of 3 different models. The alfresco model, which stands for the Alaska Frame-Based Ecosystem Code, which is a fire dynamics code, the TEM model, Terrestrial Ecosystem Model, and the GIPL, which stands for Geophysical Permafrost Lab model. And all these are based, alfresco and GIPL are based here on campus. In the first phase, the pilot phase, we did a coupling of these models in a linear way, where the alfresco ran for 100 years, passed its outputs onto the TEM model, and they ran for 100 years, and then the output of TEM went to the GIPL model, which then ran for 100 years and then produced all the outputs. In our phase 2, we have a cyclical coupling, where the TEM model and the GIPL model are exchanging data on a monthly basis, which then interfaces with the alfresco model, the fire dynamics model, on an annual basis, and then passes on. We are currently in this phase 2, wrapping that up. Just going on to components, climate largely drives the IEM, air temperature, humidity, precip, vegetation distribution, slope aspect, elevation. And then the stuff that's passed in between, which is important, is vegetation distribution, the area burned, and the fire severity by the alfresco model has an impact on the organic layer thickness, which is important for the permafrost model. Biomass is exchanged from the TEM model back to the alfresco model because biomass is important for fire and rates of fire. This is currently has always been the spatial domain of the IEM. It encompasses all of Alaska, most of Alaska, and into the Yukon and British Columbia. It also encompasses all 5 of the LCCs that have a piece of Alaska. So it's quite large. And this is our conceptual model of how we use it as a tool for resource managers and decision making. The IEM model runs over here. It spits out output for different resource impact models. It could be a hypothetical model, it could be a habitat change model, a fire management tool, animal performance. And so the outputs go into these hypothetical models or any of these other impact models. And the outputs of these models then go to decision makers, and they can make decisions based upon what we believe is the best possible science at the time. The decision makers and the models and other stakeholder groups interface with each other fairly regularly to make improvements to the IEM or back and forth. And so stakeholders say we need this, and we bring it back. And so there's a lot of communication back and forth between all the parties involved in this process. Here's some examples of the outputs. Just I want to show you what we're doing. Here's the initial land cover for the IEM, just spatially. All this data is available online. Here's changes in Treeline. Here's from the change in Treeline from 2014 to 2100 in the blue outline here. And on this side is just the basal area in 2100. And this gives an indication where the tree line might be advancing in year 2100. And so this information might be valuable to a decision maker or other party. All of these products are available. All the anticipated products and deliverables are available online. There's a fact sheet which goes through the climate products, the ecosystem dynamic products, the disturbance, the land cover, landscape, soil properties, and the code and documentation. It's all accessible at this website. And then there's also an indication of availability, whether it's available now or the anticipated date of availability. And so what I've been working on for the past few years is the Alaska Thermokarst model. This was inspired by Philip Martin, who is who's now retired, but he was the Arctic LCC science coordinator. And he was interested in shorebirds and their habitats. And the big question is if we have a slight change in land cover, the drainage patterns change, and the habitat changes pretty dramatically. So we can go from a wet, largely low-centered polygon environment on the Arctic coast and have this sort of habitat for this bird. A couple centimeters of land cover change, we drain the landscape, and it's no longer suitable for this habitat for this bird, but it's more suitable for this bird habitat. This is also this change in landscape also has very profound effects on both the energy and carbon fluxes. We go from a latent heat-dominated system to a sensible heat flux system. It also has big changes in carbon fluxes from a methane-dominated system to a carbon dioxide-dominated system. So there's lots of implications from just a couple centimeters of change in the landscape. And just to highlight that this change is happening and does make a difference in bird habitat. This was an article that came out in the ADN last fall, just saying that permafrost sags are changing the hydrology, favoring different plants, and they're more beneficial to this bird species. There was another article just published a few weeks ago by the USGS that was describing how climate change is impacting other species of birds in the area. So, important topic. So this is the Alaska Thermokarst model. It's over here. I have a dotted box around this because at this point it's a standalone model, but eventually we will be coupling it with the TEM model. What we will be passing back to the main IEM model is landscape type and position and its age and the size of that land cover type. Basically, it's a state and transition model based upon frame-based methodology to track cohorts, which are unique representative landscape units. And so a high center polygon would be a cohort, or a lake would be a second cohort. They're very unique and have different properties, and we've modeled those separately. We track cohorts by fractional area in each individual model element. It's not a spatially explicit model. We're running a 1 kilometer resolution with an annual time step, just like the IEM, and our goal is to simulate from 2000 to 2100 well. And our landscape transitions that we're focusing right now are on Arctic tundra, boreal forest, and Arctic lakes. Part of the ATM, the Thermokarst model, is determining where Thermokarst could happen. And so we developed a predisposition model, which is based upon the presence of permafrost, the ice content of the soils, and physiography, whether it's a lowland or an upland, and the presence of histels, which are a thick organic layer which is overlaying permafrost, which we believe is susceptible to Thermokarst. And so these darker blue areas are more susceptible to permafrost or to degradation of the landscape, and the lighter areas are less. And so if there's no possibility of degradation, we don't run the model in that area. If it is susceptible to landscape change, then we will run the model in this area. And so this data set is also available on the SNAP and the IEM website. And so the ATM goes through, has a two different frames that we've been focusing, the Arctic tundra and the boreal forest. Each one has different processes of change in different cohorts and different ecosystems. The one I've been focusing primarily is this Arctic tundra, but I am starting to work on the boreal forest at this time. Within each, so just focusing on the Arctic tundra, we have three different ecotypes: the wetland tundra, the graminoid tundra, and shrub tundra, which can move back and forth through different processes: shrub expansion, ice aggregation. Thermokarst can move it back downwards. And then within each ecotype, we have a landscape type. So we have a low center polygon, or a meadow, which is a drained lake, or a high center polygon. And so in this landscape moves through here. So we have different landscapes within each ecotype. Then we also have lakes and ponds, which can cycle back and forth through each other. Or we can have some drainage, and then we can move back into the wetland tundra. Similar sequence of things happens for the boreal forest, but different ecotypes and different cohorts, which go through different processes and changes and have different rates of change. So these are just examples of some of the landscapes that we are trying to simulate. Here's a drained lake or a meadow. The ice wedges have been degraded and thawed. Here's the low center polygon, which eventually will evolve into a high center polygon. So this is for the Arctic tundra. And then for the boreal forest, here's some bogs with some islands of spruce and birch islands. Here's a gradient of bogs going from old bog to old fin to young fin to a permafrost plateau, and then just some old bogs. So these are what we're looking at simulating. And so no matter which system, the boreal forest or the Arctic tundra goes through, at each time step, each cohort goes through a decision tree where we ask different questions, and the landscape can evolve based or not evolve based upon the answers to these questions. In this example, we ask questions such as, is there a major climatic event which may cause overflow and drainage of a lake? If yes, then we go one way. If not, then we go another way. Is the active layer of the amount of seasonal thaw, does that penetrate into ice-rich soils? If yes, then we'll thaw and slump some of the soil. If no, then we'll move on. And then the final thing is the climate favorable to a change in ecotype? So can we move from a wetland tundra to a graminoid tundra in a fractional way? So we go through a series. So each cohort in each element will go through a decision tree for every time step, which is right now the Arctic tundra model has about 50 cohorts that we're looking at each time step, and the boreal forest has about 10 to 12. So here's some expected outputs. This is a test area of the Barrow Peninsula. Here's Barrow itself and the spit jetting out. Just to give you an idea, it's about 2,000 square kilometers. And so here's the fractional area of lakes in 1950. Lighter areas are higher percentage and darker or lower. We have these spatially distributed files on annuals. Here's some low center polygons. And then here's just the dominant cohort, whatever has the highest fraction in each cell. So this spatial data, here's some changes decadal over time for a single cell near a lake. And so we can look at changes which may have changes in the habitats or other decisions. And so where we're at right now, we're about to start our phase 3 of the IEM project, which will begin on September 1st. We're focusing on the code completion and coupling, and then after that, in the second year of that, we'll start applying the model to very specific resource needs and have specific projects, mini projects. The ATM is working on the Arctic Coastal Plain and the Yukon Flats and Tanana Flats currently. Next year, we'll start on the Yukon Kuskokwim Delta and the Seward Peninsula. And then finally, the Alaska Science Center will be starting a pilot project where we'll be working with the Arctic and Western Alaska LCCs to interface with bird modelers to make sure that our outputs are compatible for their models for bird habitat modeling. Here's our website if you're interested in more you'd like more information. And with that, I'll show you a bad logo, and it's Alaska Climate Science Center logo, and I'm happy to take any questions.